Okay, well, welcome and thanks for coming to yet another graduate seminar. We have me talking about the ends of spaces. So without much further ado, I'll hand it over to our speaker. So yes, we'll be talking about the ends of spaces today. I think initially I was supposed to talk about ends of groups, but due to scheduling conflicts, I had to find another talk. So I just kind of had to I decided ends of space is actually interesting enough that it self-deserves its own talk. You missed all the important bits. I'm sorry.
I busted into the wrong room.
Yeah.
It was real awkward.
So ends of spaces. As a caveat, I wanted to initially talk about the different definitions because there's a lot of them, but it turns out that even though there are a lot of them, there's only a couple that have been used in any meaningful way so far. There's some generalizations that I looked at that I could have talked about, but I didn't see any results that stemmed from them. So instead, I'm going to be specifically focusing on the original notion, Freudenthal's definition of ends of spaces, and then next week, I'm going to continue on in the groups where it's going to be a specific case of the ends of spaces, where we're going to use an equivalent but different definition that specifically fits for geodesic metric spaces. So let's see, where do we start? What are ends, I guess? So Hans Freudenthal, I think he's German, in 1930 introduced the notion of ends in his dissertation, PhD dissertation. He was studying topological groups. So he was trying to find invariants, ways to categorize them. But I think before we get there, I do want to, if time permitting, I do want to kind of finish with a major result of his. But before we get there, I kind of want to give like a geometric interpretation of the ends of spaces. It's way more tangible. I think if I wrote down the definition, a lot of people would be like, what are you talking about? So if I first show you the geometric definition, and maybe we can even construct it together to figure it out. I think a lot of people saw this drawn in the chalk room last semester for no reason. Finally, it's come to fruition, this talk. So if I drew a subspace of R2, so basically all of this area here, and goes off into infinity in these directions, without any notion of what ends are, if I just asked you how many ends does this space, well, how many do you want it to have? Three, right? Yeah. So that's exactly what we're trying to rigorize here. How do we tell math that the space has three ends? So let's see, we can say, well, let's look at all the directions we can travel to infinity. Well, I can go, I guess, in this direction. I can also go in this direction. But I can also do this, right? We don't want these two directions to denote two different ends. We want them to somehow be equivalent. And what's something obvious that pops out about those two directions? How can we say that they're equivalent? Well, one thing is, it seems like, let's say, I don't know, Abril and Bryce are traveling in those two directions. And at any point they decide to talk to each other, they can just walk over to the other person and they can kind of communicate, right? They can talk to each other. So we don't want, whenever we have that, we want to kind of, we want to say they're traveling towards the same end, right? Because they can communicate, their path connected. But okay, so now the problem is, let's say Abril does this. Decides to go in one direction, and does a switcheroony, flips once, and then goes in another direction. Should we consider these two the same ends? Yes, right? So we have to kind of find a way to we have to kind of find a way to say that this direction. Sorry, let me draw this way. We have to find a way to say that this direction is inherently different from this, even though at any point Abril could just turn around and come back. So what's a way to stop that? What's a way to stop Abril from turning around at some point? So in very weak notion, we're not going to use any topological terms right now. We could put like doors, right, behind them. We can say we're going to close some doors behind you after a certain point. We're going to close these 3 doors. Maybe I should write the name. I forget I have to be professional. Okay. So yeah, right. So we close some doors behind them, and we say you can do whatever you want, but at some point you're going to have to pick where to go, and then the doors are going to close behind you. So you can mess around, you can go back and forth, but then at some point the doors are going to close, and you have to decide where to go, and then we're not going to let you back, right? So
Yes, if you go off in one of these directions to infinity, you can't in particular keep going back and forth through any one of these doors.
yes, right. And the way you're putting it, this is the reason that I'm doing this really funny bit right now. The way you're putting it is going to help a lot with next week's definition, which is equivalent, and that's why I'm doing this whole thing. Anyways, so right, that fixes some issues, but does it fix all of them? The question. So let's say we put doors, and we say once we close the door, you choose something, and then all the different paths that a Brill and Bryce could take represent all the different ends of the space. Is that true now? Could we find any reasons why that could fail? What else could a Brill and Bryce do? Yeah. Um, don't spoil anything. That's, that's
we ought to just keep going in a circle.
yeah. We'll get to that. That's what we're gonna fix later. But yeah, we can just mess around and go in circles forever, right? Just do whatever we want. Never go off to infinity. So that's one issue. The other is you have to. I mean, to define where to put the doors, you're gonna have to figure out where the ends are, right? So it's kind of like the definition has to know what an end is in order for it to define it. So that's another issue. Another is 3 doors is probably might not be enough, right? Again, like what if there's a branching off here, and you've drawn way too little? You've only drawn 3 doors. Now, if a Brill and Bryce decide to both go in this direction, the door closes behind them. They're both stuck in the same end, even though we don't want this to be true. We want there to be 2 ends here, right? So we want an arbitrary number of doors. We don't know where to place them. We also want to fix the fact that they can stay in here forever. I think an elegant way to fix a lot of these is to find a way to basically flush them out. Say, you've been here for too long, get out of here. Keep flushing them out. You know what I mean? So
Maybe a collection of compact sets that is bigger and bigger.
don't spoil anything. You're right. That's exactly it. But I thought a cooler analogy is that. Oh, let me add myself in there too. So Panis is also in there because we need 3 people going in 3 ends.
Are you going in circles or are you going somewhere?
I haven't decided what to do yet. But the circumstances are going to decide for me, because what's happening is that we are in like an ancient tomb tunnel system, and we're trying to steal a precious gem. We just took it off from here. We stole it from here, and once we took it, the place started getting flooded. So it's a flash flood scenario. So after a certain amount of time, all this area is going to be just water. So we need to decide where to go by that point, right? So we're going to have to be here. You can choose to be here. I can choose to be here. You can choose to be here. And then after more time, there's more water. There's more water. And here you have to make a choice. You have to decide where to go. And this way, you don't have to decide where to put the doors. The doors are going to naturally get everywhere. It's going to cover the whole space. Wink, wink. So that would have been better if you didn't spoil it. Right, so that's how we fix the problem, is we flush them out. And so now our definition, if I write the definition down somewhere, would naturally follow. Can I still do it here? Okay. And maybe I'll start. Good?
That works, yeah.
Okay. There's barely any tip here, but it's okay. All right, first off, we have to define like the space that we're going to be operating in, and generalized continuum. When I write generalized continuum, know that it's just a really nice space, because there's a lot to. It's locally connected. It's locally compact. Let's do here. It's connected. And also what? Hausdorff, yes. It's sigma, sigma compact, and it's Hausdorff. Okay.
Remind me of sigma compact. Is that different from locally compact?
Yes,
Yeah.
sigma compact means you're countable union.
Okay.
So it's, yeah, the whole space is just a countable union of compact sets. And the thing that Bryce was talking about earlier with having nested sequence of compact sets, that's guaranteed if you're locally compact and sigma compact. So let's now write down the definition of ends. Who put this table here?
Yeah.
So given a generalized continuum X, let's take a sequence of compact sets such that the union of the sets covers the space and they're nested. So the interior contains the last one. Okay. So right, we have this sequence. Then we define an end is a sequence of.
Sorry, the mark is sort of dying again.
Oh God. Okay. All right.
It's
Let's see.
showing up on some.
This is not going to be any better. It's okay.
You're gonna have the Dima situation where you're gonna get like.
Do not swear at the previous lecture.
Exactly. In every two sentences you just.
Okay, maybe that works better.
Bhavni to the rescue. Thank you.
The savior. Thank you.
See, this is why you need to study a colorful subject like knot theory. You just have like colorful markers all the time. Okay, so an end is also a sequence, such that now this way the inclusion goes the other way. So it's a nested sequence. I'm writing this too big, aren't I? Such that, yeah. Okay. Cn is a connected component of x minus kn. So you have these compact sets. So this is your compact set. And then you look at the set difference, so just like the three things that go off, and then you pick one of the components, and then you do it again. You take the bigger compact set, you look at the set difference, pick one of them. So every single time you're making, Abril, Bryce, and I make a choice where to go. So these choices define the ends of the space.
Assuming that they stabilize, so that at some point after some number of steps, we can be sure that we have the same class of, because if you kept deleting more components and you kept getting more and more ends,
You can have infinite ends.
yeah.
No, but this is just true. You actually, spaces can have infinite ends, and it turns out that any space with.
That's why the sequence bit is important, because you couldn't just like stop it.
Oh yes, yeah, right. Okay, so let's see. Right, blah, blah. Okay, so we've defined the notion, and also now you might be wondering these ends. Let's denote the end space of X. No, I don't know. Okay. Like this. Note that I haven't denoted the sequence that we started with here. And that's because we don't need to. They're all homeomorphic. You can start with any sequence. You'll end with homeomorphic end space. So that's our first. Maybe I'll write that down here. Should this be a theorem or a lemma claim? I'm not proving it.
So sorry, I missed. You're defining it as object called an end space?
It's sorry. Yeah,
It's these collections of.
Maybe I should.
CN.
Yeah, exactly. Sequences CN, where they are these connected components of.
Right.
asking.
Yeah, you remove
Yeah.
these compact
It's
sets.
So on
a
and so
connected component once you remove KN.
Yeah, you just keep taking these
And
sequences,
so
whatever.
then, what did you want to state?
Oh,
Well, he wants to say like the choice of sequence of compact sets that we use to define all these
KN?
ends. Yeah.
that's you don't the choice is arbitrary. You still get the same n space. It's all
Doesn't
on
matter
work.
which one you pick.
So I guess I'll say here, just say fact. Given
You might be concerned from the way that you wrote n to x there that like, all right, you should be putting n to x kn.
Right, right. So if you get, say, for example, you call KN prime, right? This induces CN prime, and is what he's
Exactly.
saying
What he's
that
saying is
CN
there's a map, a natural map between these two different spaces. These
natural
spaces
map or
sequences.
homeomorphism?
the homeomorphism, it's the
Natural.
natural map.
Let me use the word natural. All right, but yeah, there's a map between them so that it doesn't matter which of these you chose.
Okay.
The n space induced by k1 of x to the n space induced by k. Oh yeah, you told me how to use
No, I
this
can
part.
totally say this is a natural. This would be a natural isomorphism.
It's very natural.
Yeah.
Yeah, you're right. Can I just not use like below this, or I can still do?
Just, fine, you're
Okay.
Don't use below.
I had one job, such that
It's hard to lecture and keep track of expressions.
is a homie. He is a homie, which is what we want, because we're trying to construct essentially an invariant here. We're trying to construct a topological invariant. We want as many homies as possible. So what is the topological invariant? Maybe we should talk about what we can do with the ends first, and then we can talk about the invariant. One really useful thing to do with ends is end compactification. So like we've like compactified spaces before, right? And why do we normally do them? Because our
Spaces are awesome.
yeah, our space wasn't compact enough. Like we want nicer properties, so compact spaces are awesome. But this isn't just any compact space. Actually, end compactification has a lot of maximal properties that we can get into. But yeah, we'll talk about how to define the compactification. So obviously, maybe should I define what a compactification is first? Yeah.
Yeah.
Before you go into that, so you said, of course, this sequence isn't in case there's an infinite set of ends or whatever.
Yes.
But
Oh, no, go ahead.
I guess given an end that doesn't have any other sort of branch, how do you exactly see that in the sequence? Like how is that?
Oh, that doesn't have any more branches. So like this just goes on forever?
Yeah, as in, imagine that the space does have a finite.
Yeah.
How is that information encoded?
That information is coded because, well, let's say you pick a sequence of connected components and you've already kind of gotten stuck in this one end, right? So you can't escape it. You have more and more compact sets. And then, so after this set, you pick this connected component, and then you can only pick this connected component, and then you can only pick this connected component. So there's actually only one sequence after that you can go into.
If you took one of these sequences of CNs that worked, and you just started deleting bigger compact sets from any one of the choices of C that you chose, it would never become disconnected. You would only end up with one. Like it would be like he's saying here, if you just kept taking away these pieces, you would only ever end up with one of these things. And
You're not going to have two different sequences because there's never going to be a branching out, right? If it branches out, you have a choice to make. Do I go with this connected component or do I go with that one? I can never go back on my choice after.
Like you take all the possible paths and then see the sequences that they reach, and then the number of distinct sequences is the number of ends.
Yes, exactly. It's the number of distinct sequences. You have the sequence, and the end space is defined as all the sequences that you have. But you did remind me that I should say that the connected components should be unbounded, which means they're relatively compact, because otherwise you have too many ends. Otherwise, you can have
you could miss a little blob from right there.
yeah, and that blob could be an end for you. Whereas if in reality, if you did choose that path, you would be flooded. You'd be drowned.
So I think maybe Claudia's getting at this. So in general, we can have like countably many ends.
Yeah.
Can it be worse? Could it be
Yeah, actually,
Yeah, there's no reason why it has to be countable.
right. Actually, you can't have countable. I think. I think
Well, I
if
mean, you
if you
could
have
certainly have countably many, but you could also certainly have more. Like, it doesn't seem unreasonable to me that you could have more.
if you have an infinite number of n's, then the n space is homeomorphic to the Cantor
You
space.
have to do like a Cantor set kind of thing, basically. Yeah.
So you can't have countable. That's the thing. If you have infinite number of n's, the n space is immediately homeomorphic to the Cantor space.
Oh.
Yeah,
Okay.
yeah,
Oh, okay.
yeah. And that also, that's another spoiler for next time, which was I'll just say it anyways. In the notion of ends of groups, actually, there's this guy named Stalin that proved that if a group has an infinite number of ends, then it has to be uncountably many, and it has to be so on and so forth in a different way. Obviously, this is the general case. So let's see. That's actually one of the things that makes the ends of groups a little uninteresting to study. It's just like always just Cantor set. Yeah.
Well, there's a lot of weird algebraic objects where, like, yeah, as soon as you go to the infinite case, suddenly a whole lot of complexity immediately drops out. The things are now too big.
Yeah, exactly. Oh, wait till you hear about the finite case. We'll get there. It's always that the complexity seems to drop out here. But it's still really good. I think it's a good topic to study regardless. I should define a compactification first. Compactification given the topological space X. Prime is X bar is a compactification. If right, I do that, yeah, X bar is compact. Here, yep, X is embedded, and X bar as an open dense.
The open and dense bit is basically us guaranteeing that we're not adding too much.
Too much, yeah. You want to retain as much information about your original space as possible while making it nicer. And that's another reason why n compactification is a particularly interesting one to study. Let's see. I feel like I'm going to run into that. Maybe I'll delete this picture. No need for the picture anymore? Okay.
How long do we have the room till? 1:30? 4:30?
I didn't book it. We were just here.
Cool. So
If someone comes in here, we'll fight them off.
Exactly. We'll duel them. And this is the third time I'm writing it. I'm just going to write n comp. So yeah, n compactification. So we have to obviously define a basis for our new topological space. The set, obviously, okay. The set is just X and then all of its n's. So we're just adding the n's to our initial set. So the basis for our topology, this is going to be pain to define. Let's see. Union set of n's for an index such that U is, okay, so it's the set of open sets in your initial topology of X. And your EI are in the n space. EI are in the n space. And for all I in I, we have that Cn in EI. Hopefully you can still read this. Cn in EI. Cn is contained in U for some n.
So we take all of these open sets, these components that define the n. We imagine that this is now the open set that is this new open set, except it also contains the endpoint at the very
Yes,
end.
yeah, exactly, yeah. You take an R open set that contains an end because it contains one of the connected components that defines the end, and then you just add the end to it itself.
So is BX bar going to be our basis for this new?
Yeah, BX bar is our basis. Yeah.
Okay.
Um,
So as a simple example, right? If I take like R2, right, and do stereographic projection, if I do one compactification, right, my end should be cardinality 1, right?
well, this is a specific compactification we're doing.
Yeah.
So what you're talking about the Riemann sphere.
Yeah, the Riemann sphere.
Yeah, right. So that's one type of compactification, but it doesn't. It's not the end compactification. So.
Wouldn't it not though? Because shouldn't it be R2?
Oh, it does coincide. Yes, it does coincide for that case. But for example, I think the R1 case, just an R real line.
Right.
It doesn't coincide.
Oh, okay.
And in general, all of Rn, when the number of n's is only one, except for R1. R1 has two n's. Yeah, in some cases they coincide, in some cases they don't. Obviously, in terms of like one-point compactification, the Alexandrov compactification just is the only one that.
There's definitely a lot in common though between these endpoint and the one-point compactification, because in a lot of ways the procedure that you go through to make the one-point compactification is like this, except you treat all the ends as the ones. You pinch all the ends together basically.
Right, and
you could consider the end construction as basically a generalization of the one-point compactification.
It is,
if you wanted to, you could just squeeze them all together.
Yeah, and
Like sort of goal was to generalize one-point compactification.
well, his goal was specifically so it was weird because his actual paper was in German, so I've only been reading like interpretations. And what I've churned out is that he was really focused on topological groups, and he found ends when he was like working with these path-connected homeomorphism families, and he realized that if he compactifies a space in a specific way, a topological group in a specific way, the points at infinity stay fixed by the homeomorphisms. So it was a very specific motivation for him. But to answer both your questions, we will get to a theorem that talks about how the end compactification is a maximal compactification that basically encompasses all other compactifications in some way. Most other, and in some ways all other. So.
You could like a quotient basically.
Yeah, exactly. Yeah. So. Stop spoiling.
Sorry.
I'm kidding. What are we? Okay, so where were we? Yeah, this is the basis. So okay, so this is our topology. We have your end compactification topology, and one thing to note is that another fact, I guess. How much time do I have?
It's 3:32, so you have. Do you want to do an hour and 30 minutes, or do you want?
I'll do an hour because we have the next talk.
Okay.
We have our next fact. What's the fact going to be? Let's say you have homeomorphism. Then phi can be extended. It's what you would think. Right. Be extended to the compactification spaces. Right. And more specifically.
We achieved Freudenthal's dream. It is in fact the topological invariant.
Yes, exactly. That was the next point. We have that I'll say it after I write this. Induces a homie from the n space of x to, sorry, Abril, I'm going over. The n space of x to the n space of y. Okay. All right, I'll get rid of this. And then
No, actually, you can read it, so it's fine.
Okay, that's good. So right, as Bryce pointed out, this just tells you that the number of n's is a homeomorphic invariant, which we can't have enough of. We need more homeomorphic invariants. Okay, so I think next order of business is probably defined. All right, maybe let's talk about why study ends and compactification in specific. Why? All right. Which begs the question, why study topology anyways, altogether? Although I've heard that that's a question you save until like a midlife crisis or something, so we'll wait. We're not there yet. Why end compactification? So one of them is obviously it's a homeomorphic invariant. Okay. But it also has some other cool properties. So I'll state this here. I have no clue who these theorems are by. I know that.
Not Hans?
No, I don't think this one's for Hans. I think he defined it, he compactified it, and then he had a lot of notion. He had a lot of theorems in topological group theory, but nothing about. I don't know about.
So this came later after Hans.
Yeah, yeah. A lot of things came after Hans. Is the Cantor space thing? I think it came after Hans. Even though I think he had like some version of it, but the most general one came after him. But yeah. So theorem one, what was it? Why is it? Yeah. Okay. So given a generalized, yeah, we're always talking about generalized continuums, continui, whatever. Continua, gencons. Given a gencon, we have, okay, so right, x and a compactification y with, oh, I should probably say, with finite remainder. Remainder I'll define right now. Okay. What's that? No, it's just the set differences.
So this is on finite.
Yeah, yeah. It's finite many points at infinity. Let's give us the finite remainder, blah, blah. What was the point? Yeah, the point is y can be identified by by x bar quotiented by an equivalent relation where the equivalent relation is on the ends, yeah, on ends of x. So this is what you were talking about earlier.
So I think this is what Claudia was saying. The number of remainders is equal to the order of ends.
That is the, yeah, it is in the endpoint compactification. Like when you define the remainder, it is the number of points at infinity. That is the ends. Okay. But in general, this is just a compactification. That's not the end compactification.
Right.
So
it's just some compactification.
yeah, right. In some compactification, you just take the set difference. You still have the points at infinity. That's what you have. But yeah.
But what you were always doing is just identifying gens.
And wait, so
yeah, yeah.
is X bar a different compactification?
No, it is the endpoint.
X bar is the, yeah.
The endpoint compactification.
Yeah.
Okay, sure.
Maybe
Oh,
should
yeah,
I?
define it over here. Yeah.
Okay, okay. Yeah, X bar is the endpoint, Y is the arbitrary compactification.
I don't know if you got main
Oh yeah, so this...
It is literally the cardinality of that set.
It's the compactification space minus the X space, so it's the number of elements in this. So how would I say this? So Y is the bigger space, right? And X is your original space. You take away X, and what's remaining, that the number of elements is finite. In that.
You know, when you compactify, how many points did you add? That's exactly what that finite remainder is.
Oh, I see.
It's also, I think, another name for it is corona. So I should have used that.
Corona theorem?
Yeah,
Even with
Oh.
yeah, whatever.
Okay, let's do it. finite corona. Okay.
You would probably ask why you call it corona, but no, it kind of makes sense. It's like peaks.
Or is there something?
I don't know. Like there's a corona theorem from complex analysis.
Oh, I see. Okay. 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 That's why. Now you know. So yeah, the idea is that given a continuous function from your endpoint end compactification to y, you can first pass this function projected to your quotient space on some equivalence relation, and then you could send it back to this space and prove that this is homeomorphic. That's the idea. So this gives you a couple of obvious corollaries. I don't even know. I think Bryce will try it out before I write it down, but I'll try my best. Yeah.
So this community diagram is saying that if you know how to embed x bar, this quotient topology into y, it induces a map out, right? If I read that correctly.
Oh no, it's the other way. So yes.
So if I know how to embed x bar into y, I can always decompose into this projection composed with. Okay.
Yeah, and this is I was just giving you like the gist of like how the proof would go. So basically, you would find a clever way to define, because this is also compactification. So you can like obviously make all of x the identity in this way.
There's a pretty obvious choice for what this map F should be.
Yeah.
You know, you have the map from X to Y, obviously, because Y is compactification. But then, like, where do you think you should send the endpoints? You know, the obvious thing kind of comes from the answer from the theorem. Like, you're going to send any endpoint to like you might end up sending two endpoints to one thing, yeah, exactly.
Right.
But there will be these things in the finite remainder that you can send them to, and there will be only one choice for thing we can send them to, where it will be continuous.
And where do you think the equivalence relation comes from?
Yeah.
If they both send it to the same point, they're equivalent.
Exactly
Yeah.
equivalent, yeah.
So when you say the compactification of y, is that an end compactification or no?
No, just an arbitrary. It just satisfies this definition of here that there is a map from X into this Y. It's an open dense set, and Y is compact. That's it.
Yeah, so I think I should reiterate like the general gist of what I'm trying to do here. So when I say y and compactification, I'm trying to show that end compactification behaves really nicely when you compare it to other arbitrary compactifications. So y is just a compactification. The only requirement is that it has a fine corona, and then you have all these nice properties that just fall right out.
This theorem basically says that as long as we're only compactifying by adding finitely many points to our space, the only thing you can do is take the endpoint compactification and maybe put a silly hat on it afterwards.
Right, right.
You dress it up in a disguised mustache, because it's still the same thing.
You first find all the ends, and then you make some of them look like each other.
Exactly.
That's the idea. But it's a cool little theorem. I was going to say something. I forgot what. Yes. Okay. So obviously follows out a couple corollaries. Is that
Corollary.
No, wrong.
Yeah, O instead of an A after the R.
Oh, you're right. Yeah. Corollary. So again, given generalized. Oh, should I? No. I'm too grown for
Dude,
that.
I got to see a lot of professional mathematicians in Montreal pronounce it corollary, which is quite something.
All right, screw it then. Corollary. Okay. So again, given Gen Kant.
You guys only just noticed that?
I don't know why you're laughing. What are you? Gen Kant. Grow up. Given a Gen Kant and a
Doubling down, that's fine.
with, oh yeah, finite, blah blah blah, corona. Well, we have. I don't know. I feel stupid writing this, but okay, let's do it. The size of it is obviously less than or equal to the n space.
Yeah.
So the reason I wrote this is because a lot of nice, like, you can use this a lot of times. That's why I wrote it. It's an obvious fact, but one cool thing about ends is that they're really, really easy to compute in a lot of cases, especially if, the space itself is nice enough, it's a Gen Kant, but if it's even nicer, geodesic metric, then like it's really easy to compute these things, and you want easy to compute invariants that also have some sort of maximal property like this. Okay. All right, let's see. Yeah, there's another. Let's talk about more maximality. Let me see how much time. Okay. I did want to prove a theorem, but okay, I'll state this quick. Theorem 2. This time, given a given any compactification y, so now there's no restriction on your y, and a specific sequence from your n space x. You have a couple things that fall out. The intersection, let's go with this, of the closure in y of your connected components is is a non-empty connected set in y difference x. So this is for any arbitrary compactification. You have that if you take the closure and you keep going towards infinity, there's going to be a point at infinity there, regardless of which compactification you use. The ends are that important. And this is almost like saying, if you want to compactify something, you have to plug the ends. Like, there's no other way. You have to plug the ends. If any end is loose, it's not compact anymore. And something else that falls out is also that, can I even write here?
Yeah.
Okay. Something else that falls out is that the corona of y is just equal to the union of all your ends. No, I'll write this. Same thing. Cn, all the ends in your n space of x. Then again, same thing. Closure in y of your sequence, your connected component sequence. So not only do you have to plug the ends, but literally that's all there are. You take them and you get. So this is the thing is like I read the proof and I wanted to maybe give out a slight caveat. In the proof, they used the fact that these arbitrary compactifications are Hausdorff. That's not given, right? I don't know if I missed something implicit. It doesn't seem given, but they did use it in both of these proofs. So that's just something to, I guess, keep in mind. Well, yeah, we'll keep your noggin jogging for a bit. Okay, so we have that. All right, any questions so far? Because I think I have just enough time to maybe sketch a proof for a specific theorem. Yeah. Yeah, I was talking about the compactification of y, compactification of x, which is y, and that's not necessarily Hausdorff. So I tried to prove it myself without using it, and I couldn't. So
Can you compactify a Gem-Klein space with arbitrarily many remainders?
Arbitrarily many remainders?
Yeah.
No, because
Look
at this.
Okay, so it gives you, okay.
Unless you have ends if the n space is infinite, then
Right.
I guess you can.
I'll ask you after.
Okay. All right, I'll get rid of this. Maybe. Do I keep any of them? No. invariant. All right, let's talk about the one of Freudenthal's first results using. I think this was 1930, but I'm going to put an S next to it. Using the notion of ends, which is that a path connected topological group has at most two ends. Okay, so this is another thing that makes, remember I told you the finite case also kind of sizzles out some ways. So more than one way it actually sizzles out. But I think I've justified the idea of ends enough. So right, this is one of his first theorems. He went on to publish more about how ends can be used to study topological groups, and then he studied how topological groups acting on spaces can be used, the end space of both of which can be used to study the space itself. So he even found some correlations between the end space of the group that's acting on this set and then also the space on the set, the end space of the space on the set. All right, let's talk about proof. I'm going to write proof sketch because this is literally actually going to be proof sketch. Okay, let's see. Okay, so first observe that for, let's say, group X. If you have an X, an element of your group, then let's say for this left translation is a homie. So multiplying by the left side to the left side is a homeomorphism. And because X is connected, I think which property gives you this? Let me think. No. No. I wanna. Oh no, it's the one that I talked about. I want to extend it to the compactification, which you can do. So because it's a homeomorphism, you can extend it. So let's left translation is a homie.
Exactly. You can extend homeomorphisms between the original spaces between and the compactification side.
Right. So then I'll extend X to R. And since our group is connected, it's actually path connected. I'm not sure if this is what guarantees it, but I think it's the connectedness of the group gives you that the homeomorphism is isotopic, or it's homotopic through.
Yeah, if it's path connected, then this homeomorphism that we have to have, yeah, it has to be isotopic to the identity.
Yes, okay. So I'll just write the result. So then fx through homies. So, and that just means isotopic, hopefully. So, all right, and then also you can extend this. You can extend the isotopy to your extend. Okay, well, I'll just do this. Extend to this thing being your extended homeomorphism being isotopic to the identity on the closure. The compactification. All right.
Sorry, what was black 14 X?
Identity.
Identity.
Yeah, the identity map. And here it's the identity map on the compactification space.
Writes their
ID, yeah.
with the D capitalized. That's just.
All right.
That's just
You
crazy.
use capital I.
Fine.
Oh my God, that's even worse. That hurts. There we go.
All right.
Now it's recognized. Now I know exactly what he's saying.
Do you want me to
Even
This is
better.
gonna bother you
Even
more?
better.
All right.
That's so good.
All right, stop being a child.
That's crazy. Psychotic.
All right. Extend, sure. So we have this, and here's the thing. So one thing I should have noted before, actually, is that the n space, maybe I should say this now. Is what?
Cardinality. It's end of x, yeah?
Yeah, that's the end.
I mean, you defined it over here, yeah?
I did.
That makes sense.
Oh, yeah, that's fine. Yeah.
Yeah. It's one of the reasons that makes it so general. Right, so this is totally disconnected. So if you have an isotope, a homotopy that you can extend, but whatever you're extending to is disconnected, you obviously fix the points, right? So then that means F fixes all of your ends. There you
The only cases where constructing a continuous function is really, really easy when your only choice is a constant.
go. Mm-hmm. I'll erase this. We're almost done now. Yeah. Right, so it fixes the ends, and now this is the part that we're going to kind of hand wave through, because Freudenthal then proves there exists X in the group such that for two distinct ends, E and E prime, and two distinct neighborhoods for the two ends, Fx translates the complement of U, I'll say into U prime. Yeah, I forgot which theorem I was trying to prove, sorry. Okay, so does this make sense? Okay, so now we
Everything
suppose,
that's not in one end, we can just send it into the other end.
yes, we can send it into the other end. So what does that say? Well, that says, remember you said that, because you also said this. I don't know, now you're saying two different things that aren't possible if you assume three ends. So assume there are three ends. E, E prime, double prime? E double prime. And obviously you have your neighborhoods. Prime. So what can we do now with what we just said? Let's do one of them. Let's do, let's find the x that takes the complement of u. Maybe I'll write this, maybe. Take x such that fx places complement of u into u prime union u double prime. Wait, sorry. Whoops. It places into u prime, let's say, which is one of them. But what does the complement contain? Contains what? It contains, yeah, specifically, it contains E double prime, which has been translated into something that's not, E prime, E double prime. But you're supposed to fix all the points, right? Does that make sense? So, right, so x set difference u contains the other end, which means you've actually taken u, no wait, please, u into here, right, yeah, you've taken u prime, sorry, you've taken u double prime and put it into u prime, which shouldn't happen. Does that make sense? Okay. Yeah, that's exactly time. Also, my parking permit just ran out. Any questions?
So wait,
Sorry, go ahead.
do you want to finish this?
I just wanted to say that this is a way that you can study topological groups, and then you can extend this to studying, like I said, topological groups that act on topological spaces by studying both of their n spaces. And then next week, we're going to be talking about how to define a topology that associates with a group, and then study the ends of that. So ends and groups and spaces just go hand in hand in all directions.
So you said earlier, ends of Rn, n bigger than 1, is always going to be of
One.
size 1.
Yeah.
So by your corollary, you have that. Is it true that you have that one-point compactification is the only thing you can do from homeomorphism on Rn?
For finite corona. If you want infinite corona.
Yeah, finite, because you could have possibly something even worse.
Yeah, yeah.
Saying
I see.
potentially adjoining infinitely many points.
Right.
Like the projective plane.
So you don't have any relationships. Are you going to eventually have a theorem where you have, like, say, infinite remainder, and you want to compare cardinality of the complement with cardinality of the ends?
I think, yeah. I'm not sure if that's a thing that I've read so far, but the thing that I erased here about each endpoint kind of containing a point of infinity from any arbitrary compactification is something that alludes to what you're talking about, but I don't have like something concrete. We do know that for any given compactification, each endpoint is going to have to contain, like, if you take the n compactification, it's going to have to contain one of the points at infinity of the other compactification. But I don't know about cardinality wise. Right? I also, when I was reading up on this, there were a lot of claims that I didn't see proofs for, so I didn't even I chose not to memorize them.
Because they were highly suspect.
They were suspect. They were like WordPress.com sort of thing. So I only memorized the ones that I saw the proof for and agreed with. So maybe there was something about it, but I don't remember.
But so in the preceding lectures, though, you're going to generalize a lot of these notions. Eventually, category 3.
Am I?
Since you need his head somewhere.
I have one more talk to give.
One more talk.
Do you want me to do like a series on this? I would have to learn German if I want me to do. I swear to God.
You don't have to learn German. You just have to learn enough
Yeah.
German to parse what they're saying.
I'll think about it. Yeah, I could. I think maybe I could go into like the proofs of some of these things. Maybe generalizations. There is a generalization. Remember how nice these spaces had to be, right? So there is a notion that kind of neglects all of that and uses direct limits and just like set theoretic stuff to really, to get the same notions that you want. But I haven't seen any use for it yet. But maybe if I do, I'll get into that. Yeah. But next time is going to be a specific. It's not a generalization. It's going to be a specialization. We're going to specialize this notion for geodesic metric spaces. Yeah.
I wonder if there's a relation. I wonder if there's a way to get something like a lim sup and lim in different topological spaces using ends. It's essentially what, like, the reason why you're able to characterize limits of functions of real variables in terms of lim sups and limits is because you can say, like, all right, if you don't converge, it's because you go to that end. If you go to that end,
Or the other end, yeah.
or the extent to which you go up and down doesn't collapse down. Maybe there's something. Maybe there's some generalization there for.
It's possible. only thing is that like
If you could say,
You-
like, all right, here's the furthest you've gone towards this end, and then you could say, like, I've got a limb soup and a limb in for each one of those directions, each one of the ends I could go towards to establish how far I've gone out in that direction. Yeah, it should be doing.
Yeah, I think yeah. Once we get into obviously the geodesic metric space case is going to be the easier one where you can define things like that. Once we get into, because we're going to be using like proper rays and stuff, so you already have directionality, actual path directionality, and things like that. So it's going to be way easier to define.
It's a really interesting property. It's one of those properties about topological spaces where when someone explains it to you, you're like, well, yeah, duh, obviously, the end of the space. Like, I've been looking at spaces my entire life.
Yeah,
It's
but to actually rigorize it.
exactly, to be the one to sit down and be like, hey, wait a minute, this is what I'm seeing. This is a clear and concise definition.
Yeah, and find this connection. I mean, it's funny. It's weird that this was his motivation. It's like my motivation would have been exactly what I said. Bill Bryce and I take a tour, and we steal a gem. We have to get out. That would have been mine. It's like, how did you figure this out? Any other questions? All right. Let's thank the speaker.
The question is, if you were this good at giving talks, why haven't you given one earlier?
All right.